Hola amigos, so let's continue with rate of climb, a little bit of portion that we left in our earlier lecture, and we will see gliding flight as well. And they are at 419 and 428 page number respectively of chapter 6 of the book we are referring, that is the Introduction to Flight by J.D. Anderson, 6th edition and special edition. So let's see, we were left with this graph of rate of climb. So what does it tell? That rate of climb, vertical component of velocity we know is v infinity sine theta, which is the vertical component over here for this graph, that is v vertical, and the horizontal component of velocity is vh, that is v infinity cos theta, and that is over the horizontal axis over here vh, and we have plotted the variation of vertical component of velocity and horizontal component of velocity for a given velocity, that is v infinity, at different climb angles, that is theta 1, theta 2, theta 3, theta 4, theta 5 or 90 degree. Okay, generally our intuition says that rate of climb will be maximum when theta is maximum, that is when it will climb at 90 degree, then the rate of climb should be maximum, but it is not. It is quite wrong intuition, we can say, and we will see how that the variation for vertical component with respect to horizontal component of velocity is typically like this. Okay, so from this graph, if you observe that maximum vertical velocity that an aircraft can climb with is this. Okay, so the maximum rate of climb will be this point, okay, for horizontal component velocity v, at which rate of climb is maximum. Okay, and we know that for same velocity we are looking at different climb angles. So this is an angle theta with for velocity v. Okay, and here we will have v infinity at different theta angle, that is climb angle. Okay, the same climb angle we are talking about here, and the aircraft is climbing at an angle theta. Okay, so here we will see an angle that is less than the maximum climb angle, that is theta max, and the rate of climb is maximum for an angle which is less than this theta max. Okay, and how we came to know that this is theta max, that when this velocity is plotted against vertical component and horizontal component, we are taking the tangent at every point. So tan theta will be this vertical upon horizontal. So at this angle, if we see, we take the tangent over here. Okay, because we are taking the tan of theta. So here, when the tangent is drawn over this typical variation of vertical and horizontal velocity components, we will see that this is the maximum climb angle with which an aircraft can climb. Okay, so this will be the theta max for vertical component v infinity, v vertical vv, and horizontal velocity component is v at theta max. Okay, because theta is maximum at this climb angle. Okay, here the vertical component of velocity is less than this rate of climb maximum, that is this vertical component of velocity is maximum at this point, but this is the maximum climb angle with a lower vertical velocity component. Okay, so now let's move on to the gliding flight. So in the horizontal motion, or say the steady level flight, we derive the equation of motion for the steady level flight, and also for rate of climb we derive the equation of motion. In both these motions, for the steady level flight and climb, steady climb, we know that they need a force to overcome the drag force and move steadily, that is thrust force is needed. But while gliding, or say while descending, there need not be any force that needs to drive it downwards, because the gravity is always acting on an airplane, so weight will always be acting downward. So we can say we turned off the engine, which means that thrust while descending or while gliding is zero. So here we will see that in this picture, which is showing that aircraft is gliding at an angle theta from the horizontal and following this flight path. Okay, this is the direction of v infinity, and here there is no forward driving force in the direction of velocity, therefore thrust, as I said, is zero, and this weight is acting downward, and drag will be there because the aircraft surface will produce some friction which will act opposite to the direction of flight path, and lift force perpendicular to the direction of flight path. And when we make the equation of motion for this flight regime, we see that drag force is equal to the w sine theta, d minus w sine theta equals 0 because it's a steady gliding flight or descending flight, and lift L minus w cos theta equals 0, which is L equals w cos theta. And if we divide both these, it will give us tan theta equals to d by L, because w will cancel out, so tan theta will be equal to drag upon lift. Here we have seen that tan theta equal to d by L, and it is equal to 1 by L by d. Drag we have taken downwards, L by d. And from this graph as well, we can see that tan theta, when seen from this vector notations, that drag, lift and weight when combined and shifted, okay, it will show that weight which is acting downward, lift perpendicular to v infinity at an angle, and drag in the direction of flight path, this. Okay, so tan theta for this lift and drag perpendicular, this is perpendicular. Okay, so tan theta will be perpendicular upon base d by L, which we have seen here from the equation as well. So we can say from this relation that L by d, or say that this descending angle will be minimum when L by d will be maximum. Okay, so why we need descending angle to be minimum, that is theta, flight path angle will be minimum when L by d will be maximum. It is, if you recall, it is the same design point L by d for which thrust required is minimum. Okay, here automatically we have turned down thrust to be equal to 0. Okay, here is no thrust, so theta or glide angle is minimum when L by d is maximum. So if we see that the aircraft is at an height h, okay, and we want to cover let's say some distance to reach the airport, or say a safe zone. Let's say the aircraft was moving and suddenly its engines have gone off because of some malfunction, so thrust is 0, so it needs to find a safe place to land. So what will it do? So it will have to glide, it will not dive speedily, so it will have to glide and approach the aircraft smoothly. So for that it needs to have minimum glide angle, that is theta. So theta should be minimum. Theta will be minimum when it will be close to horizontal. This is horizontal, and when it will be close to horizontal it will be minimum. When it will be like this vertical, then it will be maximum, which is not a desirable situation. Okay, so when the aircraft is at an height and the engines are turned off because of malfunction, then it will have to find a safe place to land. So the amount of range it needs to cover can be deduced by the glide angle that it will follow. Okay, at height h, okay, at height h it has a glide angle theta. Okay, so let's say this is the surface and this is the height at which the aircraft is flying. So from the surface at a height h, we saw that it is at an angle theta, and this much amount of range it can cover. Okay, thank you. Next lecture we will continue with absolute and service.